Okay, I just wanted to do a real quick video because there's a little bit different notation being used in your textbook than what I've been using in the notes. And so I just wanted to kind of highlight it. It's not something that you necessarily need to know for the AP, but when you're doing some of your homework problems, I wanted to make sure that you kind of understood what was going on there. Now, what we have done for these Riemann sums is we identified the Riemann sums as the sum from I equals 1 to n of delta x times f of ci, where ci was our selection, our choice of point within the interval. Now, what's a little different here, and this is kind of expanding the definition of the Riemann sums, is that for us, this delta x, we were assuming that the delta x was from equal width partitions, that we were dividing it so that all of our rectangles had exactly the same width. So we were doing n rectangles and delta x was the equal width that we were using. So the first kind of change that, if you notice this in your textbook, is going to be that, remember that we pretty much set that it doesn't really require that all the partitions be of equal width. And so what they've done to the formula to adjust for that is they do the Riemann sums as I equals 1 to n. You'll still have n partitions, they just won't be equal width anymore. So they do delta x sub I, which basically means that each interval is going to have a different width, and so you have to have the width for the first interval, the width for the second interval, the width for the third interval, and so forth. And we saw that in one of the examples in our class notes where we had to have different widths and we wrote it down for each one. Now the next thing that's going to be a change, because our widths are not the same. Now when we actually started doing our definite integral and defining them as this sum, when I was doing it, and kind of what you're going to be used to seeing, is that the actual definite integral from a to b of f of x dx, we defined that to be the limit as n goes to infinity of the Riemann sum, I equals 1 to n delta x f of ci. Now there's another way to think of this, is that we're looking at it from the perspective of as the number of rectangles increases. Well, there's another way to think about that, which is as I increase the number of rectangles, my width is getting smaller and smaller for each one. So another way to look at this would be the limit as delta x goes to 0 instead of the limit as n goes to infinity. You do realize that they are exactly the same concept, but just a different way of saying the same thing. Now, what the book is going to adjust for again is this fact that our delta x's are not the same for every width. So when they're writing it in this notation, they're like, wait a minute, I can't just say delta x goes to 0 because all the delta x's are going to be slightly different for each one. So what they've done is they've created a new notation. And like I said, I'm really just showing you this so that when you see it in your book, it doesn't confuse you. So we basically know that we have delta x sub I, and these are going to be the varying widths of each partition, or each rectangle. Whenever I say partition, you want to think each rectangle. And so what they've done is they wanted to kind of go, let's define a new term that describes what they're going to call the norm of the partition. And it's going to look like this, where they do this like double absolute vars, a delta, and this. And when they see that, this is going to be what they call the norm of the partition. Okay, and what they mean by that is that in the case that we're doing up here, okay, I'll do that one first. Because all the delta x's are the same, we can find that by b minus a over n. If you have equal widths, then they are essentially using this norm of the partition to be delta x. So it means the exact same thing. So if their notation, they would put this double bar, delta, double bar, that norm goes to 0 would be exactly the same as delta x going to 0. Now, when they are not equal widths, okay, so the norm of the partition when they are not equal widths, is going to be related to the subintervals in the fact that what you're going to do is that if you take b minus a and you divide by this norm, so I need more room here, and I divide by what this norm is, that when I divide by the norm, it's always going to be less than or equal to n. And so the idea here is what they're trying to account for, that creating this special symbol, that this will approach 0 when n approaches 0. And you don't even need to worry about finding what the norm is or anything. The only reason I'm bringing this up is because when you see some of your limit notations in your textbook, what they will look like, and let me get one for you and then just tell you why I'm waving my hands a little bit. What it will look like is you'll see something like the limit as this norm goes to 0, the sum I equals 1 to n, and then they'll have 2 to the negative ci times sine of ci times delta xi, and then they'll give you something like an interval 0 to pi. And they'll ask you to write this as a definite integral. And initially you might have been like, well, I don't understand what this is. You can basically take this out and think of this as the limit as n goes to, oh, whoops, I totally wrote that down wrong. I was writing it up here. N's going to infinity. So when you see this, just in your head go, they mean this. And then that will make sense when you're looking at this, that here's my endpoints that I'm plugging in. So here's my input into the function. So the function f of x must be 2 to the negative x times sine of x. Here's your delta xi's. Doesn't really matter whether it's delta x or delta xi. So when we write this as a definite integral, what we would write it as the integral from 0 to pi of the function 2 to the negative x sine x, and then our differential in x. That this means this, and don't let this notation over here confuse you simply because they're using a little bit different notation than what we used. When you see this, just immediately in your head go, they're just doing the limit as n goes to infinity, because this norm, as the norm goes to 0, n is going to go to infinity. And so it means exactly the same thing that we did. It's just a little different notation. I just find that it's easier just to use this as our notation, and the AP doesn't use the norm partition. They use n going to infinity. So you'll be fine on that.